Here we are at Lecture 10 in Tech Skill Hub's Beginner Machine Learning. We have come a long way. Today we will delve into the fascinating world of neural networks. I mean, really, what could be more awesome than a computer model that models the human brain, which itself is the most amazing computer model of all, right? This lecture will cover the basics of neural networks, how they learn, and provide an overview of deep learning. Neural networks are a cornerstone of modern machine learning and artificial intelligence, and understanding them is essential for anyone looking to work in this field. So how about the basics of neural networks, which are computational models inspired by the human brain, where interconnected nodes, neurons, process data in layers to learn patterns and make predictions, essentially allowing computers to mimic how the human brain learns by analysing and interpreting complex information. It's considered a subset of machine learning, particularly within the field of deep learning, and is often used for tasks like image recognition, natural language processing, and complex data analysis. As I said, at the core of neural networks are neurons, which are the fundamental building blocks. A neuron is a mathematical function that takes one or more inputs, processes them, and produces an output. Let's break down the components of a neural network. The neurons themselves. Each neuron receives input signals, which can be thought of as features from the dataset. These inputs are multiplied by weights, which determine the importance of each input. The weighted inputs are then summed together, and a bias term is added. The result is passed through an activation function, which introduces non-linearity into the model. This non-linearity allows neural networks to learn complex patterns. How about layers? Neurons are organized into layers. A typical neural network consists of three types of layers. First, the input layer. This is the first layer of the network where the input features are fed into the model. Each neuron in this layer corresponds to a feature in the dataset. Second, the hidden layers. These are the intermediate layers between the input and output layers. A neural network can have one or more hidden layers, and each layer can contain multiple neurons. The hidden layers are where the actual learning occurs, as they transform the input data into more abstract representations. And third, the output layer. This is the final layer of the network where the output is produced. The number of neurons in the output layer corresponds to the number of classes in a classification problem, or a single neuron for regression tasks. Here is how neural networks learn. Neural networks learn through a process called training, which involves adjusting the weights and biases based on the input data and the corresponding output. This process is guided by two key concepts: activation functions and the loss function. Activation functions determine the output of a neuron based on its input. They introduce nonlinearity into the model, allowing neural networks to learn complex relationships. Some common activation functions include: first, the sigmoid function maps input values to a range between 0 and 1. It is often used in binary classification problems. Second, the rectified linear unit. The re-LU function outputs the input directly if it is positive, otherwise it outputs 0. It is widely used in hidden layers due to its simplicity and effectiveness. Third, the softmax function is used in the output layer for multi-class classification problems. It converts the raw output scores into probabilities that sum to 1. And in addition to the activations, we have the loss function, which measures how well the neural network's predictions match the actual target values. It quantifies the error, guiding the optimization process. Common loss functions include mean squared error, or MSE. This is used for regression tasks. MSE calculates the average squared difference between predicted and actual values. Or maybe binary cross-entropy, which is used for binary classification. This loss function measures the performance of a model whose output is a probability value between 0 and 1. And of course, categorical cross-entropy, which is used for multi-class classification. This loss function measures the dissimilarity between the true distribution and the predicted distribution. Also, remember backpropagation. The learning process involves adjusting the weights and biases to minimize the loss function. This is done using an algorithm called backpropagation. During backpropagation, the network calculates the gradient of the loss function with respect to each weight by applying the chain rule. The weights are then updated using an optimization algorithm such as stochastic gradient descent, SGD, or ADAM to minimize the loss. Let's do a little math, shall we? Here is a simple example of how neural networks work in a real application. It's a perceptron, the most basic neural network. Our little system classifies whether a student will pass an exam based on two inputs, which are their study hours or hours input and their test scores score input, where the output would be pass or 1 and fail or 0. Each input being weighted and summed with a bias before applying an activation function to determine the final result, essentially deciding if the combined weighted value exceeds a certain threshold to classify as pass. Here are the key components of this perceptron. The inputs are study hours x1 and test score x2. The weights are a weight for study hours w1 and a weight for test score w2. The bias is a constant value bd that influences the activation threshold. The activation function or stop function is a function that determines the final output based on the weighted sum. Here is that calculation. So very simple, really. I think we need another talk about deep learning. Deep learning is a subset of machine learning that focuses on neural networks with many layers, known as deep neural networks. While traditional neural networks may have 1 or 2 hidden layers, deep learning models can have dozens or even hundreds of layers. The key characteristics of deep learning would include 1. Hierarchical feature learning. Deep learning models automatically learn hierarchical representations of data. Lower layers capture simple features while higher layers capture more complex patterns. And 2. Large data sets. Deep learning thrives on large amounts of data. The more data available, the better the model can learn and generalize. And 3. High computational power. Training deep learning models requires significant computational resources, often utilizing GPUs to accelerate the process. What about the applications of deep learning? Deep learning has revolutionized various fields, including computer vision. Deep learning models, particularly convolutional neural networks, CNNs, have achieved state-of-the-art performance in image classification, object detection, and image generation. Also, natural language processing, NLP. Recurrent neural networks, RNNs, and transformers have transformed NLP tasks such as language translation, sentiment analysis, and text generation. And speech recognition. Deep learning has significantly improved the accuracy of speech recognition systems, enabling applications like virtual assistants and transcription services. Finally, but maybe most important, healthcare. Deep learning is used in medical imaging, drug discovery, and personalized medicine, helping to analyze complex biological data. That is deep learning. In conclusion, neural networks are a fundamental concept in machine learning, enabling us to model complex relationships in data. Understanding the basics of neurons, layers, and how neural networks learn is crucial for anyone interested in this field. As we move forward, deep learning will continue to play a significant role in advancing artificial intelligence and machine learning applications. I know that this course is getting deep and getting a bit tougher. Maybe you were looking for a quick fix to make you a bit of gold, but remember what J.R.R. Tolkien said. All that is gold does not glitter, not all those who wander are lost. The old that is strong does not wither, deep roots are not reached by the frost, no. In other words, the value or beauty of something is not always visible on the surface, and the journey itself might be what makes our trip into machine learning most valuable. We will see you next lecture. Don't forget to like and subscribe for the sake of Tech Skill Hub and adventuring hobbits everywhere. This is Ethan signing off.